Hello, welcome to Software Pass channel. I am Godfrey. In this video, I am working out questions on Cambridge A2 Chemist. The topic we are dealing with is as further aspects of Equilibria, October-November 2019 exam series. Topical questions is the way to go, and I encourage you to do your revision topic-wise. In this way, once you read to a given topic and the content is still fresh in your mind, you can attempt the topical question that will be set on this particular topic for several years, 2019 going backwards. This will expose you to the examiner's mind, the key areas that are usually tested in that topic, and what you need to be knowing as you go into an examination situation as far as that topic is concerned. This is a sure way of getting your ESTA, and of course after you're done with the topical question, then you can give a shot to full past papers, time yourself, and build speed. A2 papers are basically 2 hours, and you should get yourself whether you're able to complete a full past paper in 2 hours. And that way you'll be assured as you go for your exams. Let me say that, guys, it's great that you're watching this video. If you have not already subscribed to my channel, please click the subscribe button and hit the bell icon below. This way you'll be notified every time I upload a new topic, new video for a given topic. I will therefore decide to get started. Always check out this tells you which paper this question we are solving was set. This was paper variant 4.1, and this was question number 5 on further aspects of Equilibria 2019 October-November exam series. Very well. Let's get started with number 1. Silver sulfide. This one is very insoluble in water. The word here is very insoluble in water. Write an expression for the solubility product KSP of silver sulfide salt. Of course, to write this, you need to write the solubility product. Of course, this one here, you need to write the ionic equation of dissolving silver in water. So silver sulfide, which is insoluble in water, will dissolve silver sulfide, will be a reversible reaction. When it dissolves, you get 2 ions of silver plus 1 ion of sulfide there. Of course, in solution it will be aqueous, but remember it is very insoluble. It will only get in solution very little of it. Therefore, we have our reactants and our products there. So the concentration of the products will be on the left hand side. And remember, this is solid. The concentration of solid is usually taken to be 1. So the solubility product will be concentration of silver ions squared, because there are 2 here, 2 moles, times the concentration of sulfide ions here, concentration of sulfide ions there. Of course, you may go ahead and divide by the concentration of the reactant, which happens to be silver sulfide solid, but the concentration of a solid is constant, and therefore it's 1. Therefore we just take the concentration of the silver ions times the concentration of the sulfide ions. That is the solubility product expression for silver sulfide in water. Part 2. Solubility of silver sulfide solid in water at 298 Kelvin is this 1.16 times 10 raised to the minus 17 moles per dm cubed per liter. Calculate the numerical value of the solubility product of silver nitrate at 298 Kelvin. Of course, when you're given this here, we know that the concentration of the sulfide ion, is 1.16 times 10 minus 17 moles per liter, and the concentration of the silver ions, which are squared there, this means twice, so it is this times 2, which will give us 2.32 times 10 raised to power 17 times 10 raised to power 17 moles per liter. So the solubility product of silver sulfide therefore will be 2.32, the concentration of the silver ion, of course squared, times 1.16 times 10 raised to power 17 minus, and the correct evaluation of this will give us 6.24 times 10 raised to the power minus 51, and this is moles. Since we are multiplying, moles cubed, dm raised to power 9. Remember, for every 1 mole, that's why we say for every 1 mole, could be mole or molecule of silver sulfide, we will have, we get, when it dissolves now, we get 2 silver ions and 1 sulfide ion. Alright, so the solubility product here will be 6.24 times 10 minus 51. How do we get to this moles? So basically it is moles per dm cubed squared times moles per dm cubed. Of course, this would give us moles squared dm cubed raised to power 6 times moles dm cubed. So this and this would give us moles raised to power 3, minus 6 and minus 3 will give us dm cubed raised to power 9. That will be the unit, though we are not asked the unit there, so just leave it at that. Let me just do away this. Part 3, calculate the minimum volume of water. Calculate the minimum volume of water needed to dissolve 1 gram of silver sulfide under the standard condition. Of course, first thing you need to get the relative molecular mass of silver sulfide, which you get as 247.9 when you do correct calculation. So the moles of silver sulfide in 1 gram, you get that. Moles of silver sulfide in 1 gram will be mass, 1 gram, divided by the relative formula mass, 247.9. This will give us 0.00403 moles of silver sulfide in 1 gram. And we know 1.16 moles of silver dissolves in 1 liter. We are given that right here. We are told that 1 mole, 1.16 times 10 raised to power minus 17 moles dissolved in every liter. So you bring that one down here. You say that, let me get this. we say 1.16 times 10 raised to power minus 17 moles will dissolve in 1 liter or 1 dm cubed, and therefore this number of moles, 0.00403 moles, will dissolve in how many liters. You're supposed to calculate the minimum volume of water. So we cross multiply here and say 0.00403 times 1 divided by 1.16 times 10 raised to power minus 17. And the correct calculation here will give us 3.47 times 10 raised to the power 14 liters. That's a lot of water. 3.14 times 10 raised to power 14 liters. Part B. Bromic acid. Bromic 1 acid is a weak acid. Its Ka is acid dissociation constant right there. We are told its Ka is 2 times 10 raised to power 19. Power minus 9 moles per liter. Calculate the pH of 0.2 moles per liter of bromic 1 acid. Of course, bromic 1 acid, since it's a weak acid, it will dissociate reversibly to give us hydrogen ions plus OBr ion. The acid dissociation constant in this case will be the concentration of hydrogen ion times the concentration of OBr ion divided by the concentration of bromic 1 acid right there. We are given, of course, when from bromic acid, when it dissociates, we get 1 mole of hydrogen ions and 1 mole of OBr. So we can simplify this further by basically indicating that the concentration of hydrogen ions will be the same as concentration of OBr ions. So it's basically like concentration of hydrogen ions squared over the concentration of bromic acid right there. Now we need to calculate the pH, so we need hydrogen ions concentration. Therefore, the hydrogen ion concentration will be hydrogen ion concentration. That is basically making hydrogen ion concentration subject here will be equal to the square root of the dissociation constant times the concentration of bromic 1 acid right there. We are given the Ka there, and we are given the concentration of the bromic acid right here. So we just plug in those right here. So Ka will be 2 times 10 to the power minus 9 times the concentration of bromic acid, which is 0.2 moles per liter. When you do correct evaluation, you're going to be getting 2.0 times 10 raised to the power minus 5 moles per dm cubed. Now, we know that pH, that is the concentration of hydrogen ions there, and we know that the pH is equals to the negative log to base 10 of the concentration of hydrogen ions, which happens here to be 2 times 10 raised to power 5. Okay, therefore, when you do correct calculation here, you get the pH of bromic 1 acid to be 4.69. So approximately this is 4.7. The pH, bromic acid. Part 2. Part 2. 5 centimeters cubed of 0.2 moles per liter potassium hydroxide are added to 20 centimeters cubed of 0.2 bromic 1 acid. This will be a neutralization reaction. Calculate the pH of the buffer solution produced. Alright, we need to get the number of moles of potassium hydroxide here. We are told 5 of this, so we know that 0.2, so what we need is moles of that potassium hydroxide in 5 centimeters cubed. This we know that 0.2 moles in 1 liter in 1,000 centimeters cubed, and therefore in 5 centimeters cubed, what will be the number of moles? We cross multiply, so we get 0.2 times 5 divided by 1,000. This will give us 0.001 moles of potassium hydroxide there. So let's get the number of moles of bromic acid that are in 20 centimeters cubed if in 1 liter we have 0.2 moles of bromic acid. So moles of bromic acid in 20 centimeters cubed. We know that 0.2 moles of bromic acid, 0.2 moles of bromic acid in 1 centimeters cubed, and therefore in 20 centimeters cubed, how many moles would we have there? We cross multiply. 20 times 0.2 divided by 1,000. This will give us 0.004 moles of bromic acid. Now, of course, from this reaction, we know that when potassium hydroxide is mixed with bromic 1 acid, what we get, bromic 1 acid is a weak acid. What we'll get is potassium bromide there plus water, and of course we write this one in ionic form. You get potassium ions plus OH ions plus HOBr. This will give us potassium ions plus OBr ions plus water. Of course, when you cancel the spectator ions here, the ions that are appearing both sides, can cancel this, just that. Therefore, the overall equation here will be OH plus HOBr, giving us OBr plus water. Okay. So now we know how our buffer solution will look like. So we need to get moles of bromic acid at equilibrium. So when this equilibrium is established, let me just write this way. When this equilibrium is established, we'll be having this number of moles of bromic acid minus the moles of the KO. So 0.004 minus 0.001, and what we get here is 0.003 moles of bromic acid at equilibrium. So moles of bromide, moles of OBr ion at equilibrium at equilibrium is equal to the mole of KOH, and that will be 0.001 moles. Okay, so to get the Ka, the acid dissociation constant, we know that Ka is equals to, of course, this, which is the concentration of this ion times the concentration of hydrogen ion right there, which will be from the acid itself when it undergoes dissociation, and the concentration of bromic acid there, which is calculated up here. We calculated it up here. So we plug in everything. So okay, the concentration of this we have said is 0.01 times the concentration of hydrogen, which is supposed to be finding out, divided by the concentration of bromic acid, which is calculated to be 0.003. So the Ka is of course known. We are given the Ka right here for bromic acid. The Ka is 2 times 10 raised to power minus 9. That one we know. So when we make hydrogen ions subject, hydrogen ions concentration will now be equal to, of course, be equal to 3 times, when you of course multiply this on both sides, divide by this, you get 3. So you get 3 times Ka, and Ka, the acid dissociation constant, is given as 2.0 times 10 raised to power minus 9. Of course, this would give us 6 times 10 raised to power minus 9. This is the hydrogen ion concentration, and therefore we can get the pH. pH is log 10 times this, 6 times 10 raised to power minus 9. And therefore the pH will be 8.22. The pH that is in the range of bases. The acid pH is usually less, but we are looking for the pH of the solution, of the buffer solution, so it's slightly alkaline right there. Try practicing solving these questions as I guide you. Practice makes perfect. You can get these same questions that I'm working out here from this site, solvedpapers.co.uk. The site I'm referring to is this site here. This is solvedpapers.co.uk. It's a site of CIE. It is well and enriched with CIE material. So you come to A level. Here, of course, chemistry 2019 A2 right there. Of course, you'll be brought to this page. You can get both November and June chemistry A2 topical 2019 questions. The one that we are dealing with right now is the further aspects of Equilibrium November, so I need you to download that. Of course, you can click here to get all the topicals that are listed here. Of course, when you click here, you'll be brought up to this page. 2019 is right here. So I need you to get this chemistry. Of course, you need to click here. It's almost just basically £10. You may ask your parents to help you with this, acquiring these papers. You can also get for June as well. Get as many topical question is possible for 2018, 2016, 2017, and of course you can also get them at a discount at this point. And then once you get all these papers, let's practice and get our skills honed up. Still, while on this, I also like to let you know that I also do online tuitions, for some online tuition classes at this site here, spacademy.co.uk. The site that I'm referring to is this one here. This SP Academy, Soft Papers Academy, the site I'm talking about. We offer ICT, mathematics, physics, biology, and chemistry. Take time and explore the site, but I need you to focus here. You can look at the step-by-step student guide on how to set up your account. You may also look at this video to get familiar with the online live classes. And once you make up your mind, I need you to register. Just come here and of course you register. Give in the correct email. We're going to set an email with activation code to create your account. Once you have got the email and you activated your account, then you can sign in and you can find a tutor to help you. We'll be glad to be of help to you as you prepare for your examinations. My charges are fair. One-on-one is £35. If you have 4 or more, I'll charge you £25 per hour. Hopefully, you will seek out for my assistance and I'll be glad to help out. Let's go to question number 2. Question number 2 was set on paper 4.2, and this was question number 3 of November 2019 series. Ammonium chloride dissolves in water to form an acidic solution. This is due to dissociation of ammonium ions. Dissolves in water to form an acidic solution. Ammonium chloride is a salt. When it dissolves in water, we get an acidic solution. This is due to the dissociation of ammonium ions. Of course, ammonium ions will release a proton and we'll get our ammonia in solution. So we'll have some hydrogen ions which are responsible for acidity of a solution. The ammonium ion is a weak acid. The pH of 0.3 moles per dm cubed solution of ammonium chloride is 4.89 under standard condition. 4.89 is actually acidic. Therefore, calculate the concentration of hydrogen ions in 0.3 moles per liter solution of ammonium chloride. Of course, you're given the pH here. Given the pH is that. So we know that pH is equals to the negative log of hydrogen ion concentration. And of course, the hydrogen ion concentration is equals to the 10. Of course, if I may just write this, you can take negative both sides, so you'll get log 10 to hydrogen ions. Then you take and logs both sides, then this becomes 10 raised to power pH minus pH, which is equals to the concentration of hydrogen ions. And therefore, concentration of hydrogen ions is equals to 10 raised to power minus the pH, which is 4.89. And once you do that with your calculator, you'll get something like 1.2882 times 10 raised to power minus 5. Right? We are looking at calculate this concentration of hydrogen ions here. So this is approximately 1.3 times 10 to the power of minus 5 moles per dm cubed. Part 2, calculate the value pKa of the ammonium ion. Of course, you're given here, ammonium ion is there. So the Ka of the expression of the Ka in this will be concentration of hydrogen ions right there, and multiply by the concentration of ammonia, divide by the concentration of the ammonium ion right there. This is for here. So we can get the Ka. The Ka will be concentration of hydrogen ion is this one here. You may use this one, 1.2882 times 10 raised to minus 5 times the concentration of ammonia, which is given here. As we are told to calculate that in solution of ammonium chloride. So the concentration of ammonia will be the same as the concentration of hydrogen ions. We're quoting the same, so this will be the same, 1.2882 times 10 raised to the power minus 5 divide by the concentration of the ammonium ion, which is the same as the concentration of the ammonium chloride, which is 0.03. Sorry, 0.3. 0.3. And the correct calculation will give you 5. Let me write it here. Correct calculation will give us Ka is equals to 5.53 times 10 raised to power minus 10. And therefore, to get pKa is basically a negative log of Ka. And this will be negative log of 5.53 times 10 raised to power minus 10. And when you do correct calculation, you get pKa is equals to 9.257, approximately to 3SF, 9.26. There you are. Part B, we are told a buffer solution can be made by mixing ammonium chloride and ammonia solution. Explain with the aid of an equation how this solution can behave as a buffer when a small amount of a strong acid is added. Right, so we write the equation here. Ammonia plus hydrogen ion will give us ammonium ion. So hydrogen ions are from the acid. So hydrogen ions from the acid are mopped up, mopped up by the ammonia. When you add a small amount of acid, ammonia will pick them up in solution. Don't forget the buffer solution is for ammonium chloride and ammonia in the solution, so the pH will remain the same. So no pH change occurs. Don't forget, this is a small amount of acid. When you add a lot of acid, then this buffer solution will not be of help. You should add a small amount of acid. Part 2, explain with the aid of an equation how this solution can behave as a buffer when small amount of a strong base is added. So let's add a base. A base is like NaOH, so it has got an hydrogen, it has got OH ions. So this will now be on the opposite side, plus the OH ions. When this happens, the OH ions will be picked by the ammonium ions, and this will give us ammonia and water. And basically what is happening here is that we are having hydrogen ions from this other side combining with OH to give us basically water. And this basically means that there is no change in the pH. If the reaction just gives us water, the pH of water will be just 0. So no pH change occurs. No pH change occurs, right? So the pH of the buffer solution basically remains constant. Very well. Part C. Part C. Part 1. Use the value of the water constant right there. Use the ionic product of water there to calculate the hydrogen ion concentration in pure water under standard condition. Show you're working. Alright, we know that the ionic product of water, Kw, is usually equal to the product of the hydrogen ions times the product of the OH ions. And we know that the product of both of these concentration of in standard condition is 1 times 10 raised to power minus 7. And of course, each one of these, that's all, you square that. And this will give you 1.0 times 10 raised to minus 14. Now, we are looking at, we need the concentration of hydrogen ions. Of course, we are using the value of Kw, which is the ionic product of water. So the ionic product of water, which is 1 times 10 raised to power minus 14. And therefore, the hydrogen ion concentration will be the square root of that, 1 times 10 raised to power that, and what we get is 1 times 10 to the power minus 7, which we get as that, moles per liter, moles per dm cubed. Part 2, the pH of pure water at 50 degrees is 6.64, a little bit slightly acidic. Calculate the numerical value of Kw at 50 centimeter cubed. Of course, you know the pH is a negative log of the hydrogen ions concentration, and of course the hydrogen ions concentration is equals to 10 raised to minus pH. And we are given the pH to be this, so we can get the hydrogen ions concentration 10 raised to power minus 6.64, which is the pH of water at 50 degrees Celsius, and this will give us 2.29 times 10 to the power minus 17. So to calculate the ionic product of water, you know that the ionic product of water is equals to square root of, concentration of hydrogen ion squared. And therefore, this will be 2.29 times 10 to the power minus 7 squared. And this will give us 5.248 times 10 to the power of minus 14, which is approximately 5.2 times 10 to the power minus 4. This is going to be moles. This is usually moles squared per dm raised to power 6 minus 6. Okay, there you are, guys. Those are the two questions that were set on further aspects of Equilibria on 2019 October, November. Get more papers from this site. Get more topical questions from solvedpapers.co.uk. And as I always say, if you need my help, get in touch with me in spacademy.co.uk. I'll be in a position to help you out. Hopefully I'll see you in my next other videos. Cheers.